Ladies and gentlemen, today we have the pleasure, we have the pleasure for us to introduce Valentin Calisti.
Calisti, why not?
No, sorry, Calisti. Yeah. So he did his PhD in France, in Nancy, and after that he realized that France is a beautiful country, and this is why he is here working in our institute. And today he will speak about maybe not too much positive, but anyway, about this minimization of blood damages induced by non-Newtonian fluid flow in moving domains.
So thank you very much, Sharka, for the introduction, and thank you very much for the invitation. I'm really glad to make this presentation with you today. So the work I'm going to present you is made in collaboration with Sharka and Nečas. And as you said in the title, you have many things. And I will start just to be a bit more precise about what I mean by minimization. In fact, we are tackling a shape optimization problem. So shape optimization means that we want to, in this case, minimize some criterion, which is called for us shape functional, which depends on shape, indubitably. And shape for us, let's say, it will be open subset of Rn. And this shape, actually, what we are doing is what is called PDE constraint shape optimization. It means that the shape functional will depend on the shape through the solution of a PDE, which depends on the domain. And in our case, the PDE is supposed to model some blood damage problem. So I will start with few motivation. So for patients, for people with heart failure, the use of what you can call ventricular assist devices and in general blood pumps or rotary blood pumps is necessary. But this may cause many difficulties like thrombosis, bleeding, or infection. And in our case, we are interested in, but we will be more positive later, more optimistic. It can cause what we call hemolysis. And hemolysis is basically the destruction of red blood cells due to high level of stress. You can see on this picture in these kind of devices, some zone of high production of hemolysis. Usually they are located near the blade or in place with like a few spaces for the blood flow. So mainly if you have a look on the engineering literature, hemolysis is caused by a high level of shear stress and time exposure. And so for starting to present what hemolysis is or to characterize hemolysis, we can use the hemolysis index, which is here, let's say for now, proportional to some scalar measure here of the shear stress and proportional to the time exposure. So once we have said this, we should say, okay, how to model blood in order to have an information about this measure of the stress. So for starting, I would say that blood is human blood, let's say, is mainly composed of plasma, let's say 55% of plasma and 44% of red blood cells and also few white blood cells. And you can say that plasma is a Newtonian fluid, like something more or less like water. But due to the interaction with the red blood cells, which are depicted here, and which are, let's say in this case, for a low level of stress represented here and for high level of stress here, due to this interaction, overall the blood will have a kind of non-Newtonian behavior. And you can see here that when they are under stress, the red blood cells deform and elongate, and it facilitates the blood flow. So somehow we can model the stress, the rheological law by this non-Newtonian relation for some Q here. So we use a power law in our case. Some Q strictly smaller than 2. So here, the viscosity, here you have the viscosity in blue, the viscosity will decrease when you have a high level of stress. So you have also in the engineering literature many papers trying to optimize this blood pump in order to minimize this hemolysis, but this optimization usually is like parametric optimization. So you can parameterize the angle of a blade or selecting few shape and try to optimize inside of this. And to try to at least pretend to try to enlarge a bit this set of optimized domain, we will tackle this shape optimization problem. So we will try to allow ourselves to not have any information on the initial shape and let some problem evolve to try to see if it's possible to find better shape. So this is the project. Maybe we will not arrive to do this at the end of the day, but this is the starting point. So once we have this, I would like to define the geometry of our problem. So in our case, we will consider a domain here, omega, that I will call a starting domain in R3. And we will consider actually moving domain. So I will give here a velocity field, V, which will deform the domain as follows. So this velocity field will induce a flow, which will move any point of my domain. And from this flow, phi, let's say, break away, so phi, I can define for each time step. So we consider a problem here in the finite interval 0, capital T. We will define omega t, the different domain at time t, through this flow defined from our velocity field here. So here what we are doing is like we are imposing some movement to the domain. So somehow we don't consider any elastic behavior of the arteria, but we impose this movement of the flow because we would like to be able to tackle the problem of like a rotating pump, for example. So to have an idea of we impose some movement of the domain and we can see how it behaves. So this is our geometry. Q is here our, let's say, moving domain, non-cylindrical domain. And on this, we need to define some PDE to define our problem. And as I said before, we will consider that blood is a non-Newtonian fluid. So we describe it by generalized Navier-Stokes equation, an incompressible one. So we have here the classical equation with the stress tensor, which was defined, sorry, a bit earlier. And we consider here that the blood velocity is sticking to the velocity of the surrounding or the inside moving domain. So here, U, the blood velocity, is equal to the velocity of the domain on the boundary. And once we have computed some blood flow, we will take some measure of some scalar measure of the stress here, which will fit some transport equation. So as I showed before, the hemolysis depends on the level of stress and on the time exposure. So finally, it will be modeled by a transport equation, which will follow the flow of the blood. So if you have at some time some hemolysis index, it will be transferred following the blood flow, and you have some source term which will create some hemolysis with respect to C, which is here for now not precise, but it's a kind of measure of the stress. So with these two equations, and because of this exponent in the rheological law, what we can have and what we will have later in the presentation is just an existence result. So here I got P blood, my blood problem, P hemo, my hemolysis problem, and I can solve it just in cascada. It's like not a double way coupling. And because of the non-uniqueness of the blood flow, we will consider that we have just existence of our, let's say, blood damage problem. Perfect. So now we have equation. We modeled our, let's say, blood damage problem, and we can state what will be our optimization problem. So the energy required to draw this 3D picture in the previous slides was blowing up. So from now on, it will be a 2D representing the moving domain because it was too complicated. So here we have like the starting domain evolving through time here. And before defining the optimization problem, I will define the class of admissible shape and admissible velocity field I will use. So we consider that the starting domain here will be supported in some so-called hold domain, represented here by D. So they are all defined in this domain, and they are uniformly C1. So they are smooth enough and this uniformly, so that we can extract later some subsequence of domain. We will have some compactness property from this. And it will be the same for the velocity field. They are smooth enough. They will be solenoidal because we are considering incompressible Navier-Stokes, and they will be also bounded. And from this, what we are looking for is the minimization of some shape functional, capital J here. And this shape functional depend on, let's say, our moving domain, omega and v. And it depends on it through a function here, a lowercase j, which depends on the domain and on the solution of our blood damage problem. But defined like this, I told you that I don't have uniqueness of the solution. So it's a kind of arbitrary choice, and it could be improved because it's not tackling the case of the worst case optimization problem. But because here U and H are not uniquely defined, I choose to take the infimum solution with respect to the functional I am considering. So here I say that the shape functional associated to my moving domain Q, defined by omega and V, is equal to the minimum among the solution of the problem related to Q. So once we have this kind of problem, usually in shape optimization, many questions can arise. You can think about like characterizing the optimal domain, or also if it's possible, you can try to tackle some sensitivity analysis in order to try to solve this problem numerically and have some solution. But in this case, without even uniqueness of solution, it can be really complicated. So in this presentation and in this work, we just consider the question of existence of minimizing shape. And for this, we use the classical method of calculus of variation that I will just quickly describe because it will serve somehow as an outline of the presentation. So we consider a sequence of minimizing domain, moving domain, let's say. So we take a sequence which goes to the infimum of our functional. And then, as I say, I have chosen my class of admissible starting domain and velocity field to enjoy some compactness property. So from this sequence, I can extract some subsequence converging to some domain belonging to my class. Why? Because the class of domain and the velocity I have described before, they are compact for the Hausdorff topology, which I won't describe, but you can consider it, let's say, for simplifying. If you take a domain, you can define a distance function, which will take for each point the distance to its domain, and you can see it as the topology of L infinity for this distance function. If you make the equivalence between one domain and the distance function, which is defined from this domain. And for the convergence in C2, sorry, I think it's okay. So once we have extracted some subsequence, if we show that we have the continuity of a sequence of solution, it means that the sequence of solution will converge to some here velocity field and the hemolysis index, which are solution of the limit domain. So here I don't precise for now what is the limit. And if we have some nice property on J, it means that we that we have a minimum. And I will go back to this a bit later. I just want to show an example of this. If we consider, for example, for H weak convergence in L2 or something like, or even strong convergence, we could consider like the L2 norm of the hemolysis. This is what will work in our case. We will have H2 weak convergence in L2 of H at least. So this is the problem in general. So to sum up, what we have is that we have a model of blood flow, hemolysis index in moving domain. We want to find a minimal shape. And for this, we take a sequence of moving domain, and we just want to show that the associated solution are continuous and goes to the solution of the limit domain. So from it, I can describe the plan, which is quite hard to deduce from this. So shape continuity of blood, shape continuity of hemolysis, and then we can conclude. So it's quite straightforward, actually. So I start with the shape continuity of blood. So before, I just want to recall some definition of the functional setting we need for this. That is to say the generalized Born space, because we are working on moving domain. So here I have drawn my domain Q. And for each layer, you can consider that for each layer omega t, you have some Banach space BT, which is embedded in L1 omega t at least. And we define the generalized Born space as follow. So these are L1 function in the entire, let's say, our 4-dimensional domain, which are almost everywhere belonging to our Banach space B, and for which the norm is in LR. it will be denoted shortly like this in the following. So now I can briefly give you the definition of weak solution to this problem. So I have written here the strong formulation. So what is done in a classical way? So we multiply this equation by a test function which is solenoidal. And then we obtain this weak formulation. And I just want to spend some time to explain what are the different exponents and the regularity of the function here. So we will, in a classical manner, look for a solution U, which is in L infinity L2 and LQW1Q. Q here will be the exponent of the rheological law. And from this, what we have is that from the rheological law, sorry, we have some natural growth condition coming with it. And we have that if du here is the symmetric gradient. If du is in LQ, we will have the stress tensor in LQ prime. So at least here, we would like that the test function are in some LQ, LP, let's say W1P space better than LQ prime. And then we would like that U, tensorial U, are in something better than L1, so that we can choose something correct for the gradient of eta here. And the classical Sobolev embedding from this space send U in 5Q/3. So the LQ, W1Q for this one for 5Q/3. Then the convective term will be here. So we would like eta to live at least in LPW1P for P, which is at least greater than this index. So now everything is well defined, and I will briefly give you some reference for the solution of this problem. First, in the cylindrical case. So the earliest reference can bring us back to Ledechinskaya and Lyons. In the case where a Q is greater than 11/5. And this case corresponds to the case in which I can put U instead of eta. Here is not the case because like U is living in this space and this function here. So in this case, I can have directly some energy inequality. If here, instead of having the derivative on the test function, I put it here, so I will have some term like in U grad U, I can have, let's say, less integrability on eta. So no, let's say I will need more integrability on U because I will have some gradient here. So the result holds for the exponent greater than 8/5. But then here I will just need some L infinity truncation, because if I want to put an approximation of U here, it will be just U, so I can take L infinity. And in the case which is presented here, if I want to replace the gradient of eta by some approximation of U, I will need to replace with some Lipschitz truncation. So I want eta to be like an approximation, L infinity approximation of U and of its gradient also. In the case of non-cylindrical domain, in the case of Q greater than 11/5, it was done in the paper of Jan Sokolowski and Jan Stebel, and they also showed shape continuity of the problem. So for the same setting of sequence of moving domain, they showed that the solution are converging to the solution to the limiting domain. And in the case 6/5, it was done in the paper of Nagel and Rožička. And what we started to do is like to prove also the shape continuity in our case. So as I said, we have a sequence of domain converging in the sense I have presented before. And if I take a sequence of weak solution associated to each moving domain, if you define tilde UK, and this is what will be done every time in this presentation. So here you have UK living in the moving domain, and you extend it by the velocity field VK, which is given here everywhere. So you have a subsequence which is converging, and the restriction of the limit of the subsequence, the restriction to the limit domain. So there is a mistake here. It should be just Q and not QK, of course. So this is a solution. And I have not precised here the conversion, but it will converge weakly in LQW1Q. So I will just give you a sketch of proof and then give some detail, not too much. So for this, the first things to do, the first step is to have some uniform estimate on the solution UK for each moving domain. So for this, we use the stress regularization, let's say, which were used in the paper of Nagel and Rožička. So it means that the problem is smoothed. So the stress tensor is smoothed with some parameter m. And here you can see that somehow we go back to the case q greater than 11/5. So we have also uniqueness of solution. And because we are in the case q greater than 11/5, we can directly write some energy estimate because we can take the solution as a test function and we can extract whatever we need. And from there, so what is shown in the paper of Negero-Rogiska is that if you let m goes to infinity, you get a solution of your problem for q just greater than 6/5. So what we have done is just to show that this constant does not depend on k. It means that it is uniform among the class of domain, sorting domain, and velocity we are working with. And once you have done this here, you can extract a subsequence letting k goes to infinity. And then what remains to be done is to identify the limit of the convective term and identify the limit of the stress tensor. So I just describe it a bit more. So something I have skipped, and I will do it till the end of the presentation, is that usually we work with the homogenized solution. So we have u, which is sticking to the velocity of the moving domain on the boundary. So usually we homogenize this boundary condition so that we work with w, which is belonging to some w1q0 space. So, but here I directly work with u, so I don't put more information in this presentation. So this just summarizes what I have just said. In this paper, you regularize, so you have a unique solution and you have some energy estimate here. And this regularized solution, when m goes to infinity, goes to the solution of our problem for each moving domain. And what you can do is to show that the constant involved in this energy estimate does not depend on what domain and what velocity you choose in your class. So while doing this, you obtain an energy like some estimate on the norm here of uk, solution associated to the moving domain qk. And from there, we can extract subsequences for now weakly convergent. So before extracting anything, I would like once again here to define the extension of my solution UK to the entire cylinder, fixed cylinder calligraphic Q, Gothic Q maybe. So we extend it this way by V. So we have exactly the same energy estimate on this extension, and we can extract in a usual manner subsequence. It's not necessary to look at the detail, just we will call H the limit of the convective term and K the limit of the stress tensor. So now we have some limit. So we have subsequence converging to some limit. We would like to show that this limit is actually the solution of our blood problem. So for this, we would like to pass through the limit in this equation. But if you have a look in this equation, the variational formulation of my blood problem, the test function, of course, belongs to some space depending on the moving domain. So what we need to do is to consider compactly supported test function in the first step. Because by considering here compactly supported test function, we have, thanks to some property of the Hausdorff convergence, that for k large enough, we will have that if you have some compact domain in your limit, included in your limit domain, for k large enough, it will be this compact, sorry, will be included in all your domain. It means that for k large enough, if I take eta belonging to HQK, it will belong to all the spaces. So while doing this, we can pass to the limit, and we have this. So it just remains to identify the convective limit and the stress limit. And once we have done this, to conclude, because we want this to be written for any test function belonging to HQ, we need some density result. And the density result we need is just to say that we can approximate any of this function by a compactly supported one, which is, let's say, quite classical, but we just need to be a bit more careful to be sure that this term is converging in a classical way. And for this, I don't go to detail. I have just some drawing to have an idea of how to do, because for many of you, maybe it's really, really classical, but if it's not, maybe you can have a look. So let's consider that we have our test function, which is vanishing here on the boundary. So with the Piola transform, we go to the cylindrical domain, and by reflexivity, sorry, we extend it to the interval minus tt. We cut from the boundary with a cutoff function. We smooth it with a modifier. So this is really classical. So it's like the most complicated slide of all the presentation in time of preparation. And then, of course, the problem is that we are working with solenoidal fields. So this guy is not solenoidal at all. So we correct the non-solenoidality with the Bogowski operator here. And once we have done this, we have a field which is compactly supported and which is divergence free. And we can go back to the moving domain with like the inverse of the Piola transform. But just while doing this, if you don't use Bogowski operator, usually you can have strong convergence both in the LQ, W1Q, and H1, L2 space. But in this case, and it's enough for our problem, you get this strong convergence here, but you just get a weak convergence in L2, L2 for the time derivative. But it is enough for us. So for identifying this convective limit, I will go a bit faster. So let's consider that I will skip this slide. And the idea is really to localize our equation, like to have a look on this compact here. And inside, because we are in a cylindrical domain, we can apply Aubin-Lyon's compactness lemma. And we can have some almost everywhere limits of our convective term. And so we have, let's say, strong convergence, but only on compact set, not at all on the entire cylinder. But we have almost everywhere convergence, so we can identify the limit. So it's done with the convective term. And it will be more or less the same principle for stress tensor, but this is the place where it's needed to have some Lipschitz truncation and the use of some Minty trick. But once again, I don't go into detail. So we have this same compact cylinder in the domain as before. And the whole idea is to use the monotonicity with monotonicity, sorry, it's long to say, of the stress tensor, which I did not precise before, but let's say that this quantity is positive. So if we are able to show that this goes to 0, using monotonicity and Minty trick, we can show that almost everywhere we have the convergence of the symmetry gradients of the blood solution. Just for doing this, this is somehow something we use the result already existing, but in my opinion, it's the most tricky, complicated part, is to use the solenoidal Lipschitz truncation to be able to have this information. And this is a simplification of the information, of course. Usually, in our case, we need a bit more, but let's say I simplify everything. So the idea to have this limit is to use, of course, the variational formulation by subtracting the limit problem and the problem associated to QK. But here, if we want to have this kind of information, we would like to put instead of eta u minus uk, but we cannot, of course. Once again, like u is not regular enough. As I said, du will live here, and we need something in B. So the point is to approximate, it's to choose some Lipschitz truncation, and this Lipschitz truncation will be like equal to the original field in a large domain, and what you need is to have some information of the remaining part to show that it is small enough. And then you can, as I said before, identify the stress limit. So with this, we have everything. So we have a sequence of moving domain, and we show that by picking some associated solution UK, we have the convergence to the velocity associated to the limit domain. So what I will present here, so before I just want to recall once again, because we are already slide 20 and it's been a long time. So what are we doing? Because we were really into like blood flow, but what we are doing is like to show the existence of a minimum for this. So we want to find a minimum. We have a sequence of moving domain converging. For each moving domain, we have a sequence of blood flow. So we just show that it was continuous. So UK goes to some U, which is the solution of this guy. And now what remains to be done is to show the continuity of the hemolysis index equation. And also the size of my slide, like the time size of my slide is not continuous, or like it's not really bounded. So even if it's remaining 7 slides, it will be faster than the previous one. So I am really slow at the beginning and fast at the end, so you will be quickly released. No problem. So for the continuity of hemolysis index, first I would like to define what we call the weak solution of this transport equation. So we will look for field HK, which are in L infinity. And so the variational formulation will read like this, with test function which are like bounded in C1. And with this, we just want some disregularity for the velocity field and the source term. And everything is okay because we have a disregularity from the previous problem. And here I finally describe a bit how is defined the source term in the engineering literature. So let's say that what we choose as a scalar measure of the stress for the production of hemolysis is the norm of the stress to some power. And this guy will live in L1 if gamma is in this range. And this is consistent with the engineering literature, because if you have a look to engineering paper, gamma is usually having this value. So at least we fit a bit to the engineering literature. So then for the continuity, we once again consider the sequence of domain. We take like initial data in L infinity and positive almost everywhere. And we also select for each domain a sequence of initial data converging to the limiting one. And what we show is that we have like the continuity, so the convergence of this sequence of solution to the limit problem. And for this, it's just 2 slides remaining. We just need to extend the hemolysis equation, which is defined only on the moving domain, to the like cylindrical one, to use some stability result, which was found in the literature, and just to say that the limit problem, the restriction is indeed the solution of our problem. So for the extension, it is as before. So I extend the velocity field with the velocity imposed to the domain. The source term is extended by 0, and this is necessary to have some property. And then extending also the hemolysis by 0, we can show that it is a solution to this problem. So we written with the variational formulation, it will look like this. And what we use is like a stability result that you can find, for example, in Boyer-Fabry. And so you have, with all the assumption that we get from the study on the blood flow, you have the convergence in this space of the hemolysis solution. So now we just want to be sure that H restricted to Q, our moving domain, is solution of the associated problem. So by definition of what we have chosen for the initial data, it's okay. It just remains to show this. So if I write the weak formulation, I have this for H tilde, which is defined in the entire ordered cylinder, which is holding for all functions defined on the entire cylinder. And I would like to show that it is still holding for the subdomain Q, the moving domain. And we use this classical property, which state that if you have your field, which is positive almost everywhere, here we need in this case to have like a 0 source term outside of the moving domain. And if the initial term is equal to 0 outside of the moving domain, and also of course, like this extension on the boundary of the moving domain is like really important. If you don't have it, you have no chance to have what you need. Then you will have that the hemolysis solution extended will be equal to 0 in the outside of the domain. So finally, you can rewrite the weak formulation like this, and you show that the limit is indeed the solution of what you were looking for. So what we have done is this: we have shown shape continuity of blood flows and shape continuity of hemolysis index. So now this is the last, a bit tedious slides to summarize what we did. So while showing shape continuity of blood and hemolysis, we showed that if we have a good property on one, let's say we have J positive and lower semi-continuous with respect to the topology we have defined for our convergence before, then there exists the domain. And for this, you can define the infimum, which is well defined because we suppose that J is positive everywhere. We choose a minimizing sequence, which converges by compactness. And then the only things to check differently than usual is like here, what we did is to define this shape functional as the minimum of some, the minimum among all the solution. So here we choose for some fixed m a solution which is like close enough to this infimum. So we take a subsequence, we can do it because of the entire presentation. And then by definition and lower semi-continuity, we can like bound from below and from upper part the shape functional associated to the limit domain, and letting m goes to infinity, we show that indeed omega star v star is a minimum of our problem. So this would have been the only side of the presentation because this is what we done. We have moving domain blood flow hemolysis. We have a sequence converging and we show the continuity, which allows us in our framework to conclude about the existence of domain. And just to give you some perspective on this work, we are currently working with John Sebastian Simon on the numerical application of this work, but we need to regularize it because what we do usually in order to have some numerical result is like to compute some sensitivity with respect to the shape of the PDE we are working with. But in this case, we don't even have uniqueness of solution. So we started to study a 2D problem because in 2D, first Navier-Stokes equation, 2D problem because in 2D Navier-Stokes have the nice idea to have a unique solution. This is good. And we also regularize somehow the hemolysis equation because it's easier for us to define some adjoint of the hemolysis equation when it is corrected by a small diffusion term. So then we have like we can define easier like the adjoint state. So we have some starting results. So here we try to optimize some minimal shape inside a blood flow, and this is just starting result, but at least it is something which is not equation and computation. So it's nice to see. So thank you for your attention.